Okay. Hello, everyone. So welcome to the last sessions of VMCAI'. So it's a sessions about verifications of quantum program and the probability programs. Yeah. So let's welcome the first speakers. The first speaker is Youngchan. Yeah, he's talking about efficiently verifying quantum programs with few tickets.
Hello, everybody. My name is Youngchan, and this talk is titled Efficiently Verifying Quantum Programs with Few T-Gates, and it's a joint work with my advisor, Robert Rand. The short flow of the talk will be after an intro, we talk about the logic, and then automation. And then after a short case study, we talk about the enhanced version of the automation. And then a simple application on the quantum error correction, encoder correctness, and then limitation, future work, and conclusion. So why formal verification in quantum computing? Measurement collapses superposition, which is a special feature in quantum computing. So we cannot use classical debugging techniques such as breakpoints or printing out the value. And second, outputs are non-deterministic probability distributions, which means that empirical testing requires massive statistical sampling, which is expensive. And third, it's hard to distinguish from noise from errors. So static verification is the only reliable guarantee before execution. The problem is that state space explodes exponentially. An n-qubit quantum state is a 2 to the n dimensional vector over the quantum complex numbers. So the dimension explodes exponentially as the number of qubits grow. So state level simulation is infeasible in practice. So instead, we reason about logical assertions on the inputs and outputs. We introduced Clifford and T gates. Clifford gates consist of H, S, and C naught gates. And the Gottesman-Ill theorem tells us that with only these Clifford gate circuits, we do not gain any quantum advantage because they are, the programs become classically simulatable on polynomial time. So we add a T gate here, and we get a universal gate set. Universal in the sense that any unitary transformation can get approximated to arbitrary precision using these Clifford and T gates. If we define T count as the number of T gates in a circuit, then the T count matters for compilers because T gates require high resources such as ancilla qubits or time. So compilers mostly try to prioritize minimizing T count. So we focus on verifying low T count circuits to ensure that optimization preserves the semantics. Our goal is an automated Hoare style verification with targeting low T Clifford T circuits, where with the structure where we have structure guided automation that produces checkable proofs in Rocq. We introduce Pauli and Clifford group shortly. The Pauli matrix consists of X, Y, and Z. And the Pauli group is an n-fold tensor of the Pauli matrices with coefficients plus minus 1 and plus minus I. The Clifford group is the key, consists of unitaries generated by the Clifford gates, the H Hadamard phase 8 S and the C naught gate. but it is also, it can be also equivalently defined as the normalizer of the Pauli group, which means that the conjugation of the elements in the Clifford group maps Paulis to Paulis. So this means that we only need to update the Pauli strings to compute conjugation by Clifford gates, or Clifford circuits in general. We implement a Heisenberg-style Hoare triple, where the Pauli strings are the predicates or assertions, and we take +1 eigenvector semantics, which means that the state satisfies the predicate if and only if the state is a +1 eigenvector of the predicate. And then the Hoare triple is valid if the postcondition becomes the conjugation of the precondition, where the conjugation is on the matrix semantics of the circuit. And then the soundness becomes the state is a +1 eigenvector of the precondition, then the evolved state becomes the +1 eigenvector of the postcondition. So instead of the typical backward reasoning of Hoare logic, we use forward reasoning along this conjugation. And we note that for Clifford gates, because they are normalizers on the Pauli group, the predicates remain as Pauli strings for Clifford gates, but this is different. This becomes different for T gates, which can produce linear combinations. As we can see in the conjugation identity, x gets sent to 1/2 x plus y. So the corresponding Hoare triple becomes, if we have a precondition x, then the postcondition of the T gate becomes x plus y, 1/2. And this can lead to an expression blow up with, for example, in the most bottom equation, if we apply T gates twice, then we get x plus y minus x without any term merging. So without term merging, this gets exponentially large, which will come back later. Intersection, to say something about the common +1 eigenvectors of multiple predicates, we have intersection predicates to express them. So intersection predicates represent the joint +1 eigenspace. And if we look at the circuit in the middle, this is an Bell state preparation circuit, and the above is the Hoare Heisenberg logic style computation, and the below is the state vector evolution computation. And the bold, if you look at the precondition of the Hoare Heisenberg logic style calculation, it's Z tensor I intersection I tensor Z for the precondition. And the corresponding state is 0 tensor 0, which is a joint +1 eigenvector of the intersection. And after the circuit, we get x tensor x intersection z tensor z, and whose joint +1 eigenvector is the Bell pair. The Bell pair is entangled, so it would be nice if we can be able to say about things which are not entangled, if we can tell whether they are entangled or not just by the predicates. And we can do that by separability predicates. This is just separability for a single qubit. The above is the Hoare triple, this is the circuit diagram we're going to use, and this is the Hoare Heisenberg logic style reasoning. The precondition and postcondition is both I tensor z, and the +1 eigenvector of I tensor z all looks like a state tensored by the 0 vector. The state where the state can be anything. This is corresponding to the calculation below, where you can just look at the starting point and the end point. The starting point, starts at the any state tensored by 0, and then it ends by a different state tensored by 0. So just by looking at the Hoare triples, the predicates in the Hoare triples, we can guarantee that the second qubit can be separable from the system, and it is 0 as the +1 eigenvector. This separability can be generated to non-additive multiqubits. They have to be non-additive because additive predicates, it's hard to tell commutativity and anti-commutativity for additive predicates. So we only focus on non-additive for multiqubits. And in the tool we have syntactic well-formedness, which denotes Hermitian unitary trace 0 matrices, which are dimension correct. So instead of checking matrices, we check the syntax instead. And because of this, side conditions reduce to syntactic checks, which can be discharged automatically. And by automation, we use rule chaining. Rule chaining is a deterministic forward reasoning along the circuit. We're deterministic in the sense that there is no heuristic-like proof search behavior. The input is P circuit Q, or the Q can be just a blank, or it can be unknown. Then the proof becomes a propagation of the predicate gate by gate. It starts from P and propagates through the gates and ends on the given Q or the blank. And the output is a proof with the discharged side conditions. The proofs are justified by the Hoare-Heisenberg rules, where the rules are all Rocq checkable with no external solvers involved. We have two main tactics, where the first is validate. It's a propagation of predicates, assuming that we already have a postcondition given. It fills in the intermediate steps and checks the final Hoare triple. We can use it. It's a minimal interaction for the users. And for the case where the postcondition is unknown, we have the solve placeholder tactic. It fills in the intermediate predicates and produces the postcondition, and it places the filled-in triple in the Rocq context, so we can observe how it looks like before finishing the proof. And the Hoare triple looks like there exists Q, preconditioned circuit Q, and then we do solve placeholder, and then we can observe what Q looks like before doing assumption to end the proof. An example is the Toffoli gate, which is a controlled NOT gate. It is the reversible AND gate in quantum computing, which makes it essential but expensive. We use the decomposition on the right here, which involves multiple T gates. And those T gates can make things very messy. This is the case when the precondition is I tensor Z. And if we go through the Toffoli gates, we get the messy postcondition expression here. This can be done by, if you know the postcondition, you can type it in and do validate, but if you don't need to bother, because solve placeholder does the inference for you, and you can just observe what it looks like. And we test the additive predicates by repeating T's on a single precondition X, which should return just X after 8 T's because it's periodic. But the problem is that automation does not merge additive terms, so we expect something to go wrong, which is the case on the graph on the left, which is the runtime versus the number of T gates on the previous example. You can see that it bottlenecks as the T gate grows, And we failed to verify that 8 T's is I because the system hanged after 7 gates. This is very inefficient considering the periodicity of the T gates. So this gets resolved later on, but if we look at the bottlenecks first, the bottleneck is rule chaining and expression growth, largely, where the rule chaining is works on the tactic level. So it's a bunch of applies on the inference rules, and it gives a bunch of syntactic side conditions to check. So per step, symbolic cost dominates the runtime. And expression growth, as we just saw, the term is not merged, so it blows up exponentially. And so that motivated an enhanced automation where we solved the two bottlenecks. The first part is direct post-condition computation of the direct computation of the post-condition in Galena. So we have a compute PC function where the function is a recursive function whose correctness is pre-verified. So instead of using LTAC on the inference rules multiple times, we can just use the fact that the compute PC function is pre-verified and then just let the compute PC function compute the whole thing, which is very fast compared to repeated tactics. And the second part is reflexive normalization, where we merge like poly terms with scalar reduction. So if you look at the automation versus enhanced, the automation does not merge terms, so after T gates, we get what we saw, x plus y minus x, where the x can get canceled out and y can get merged, but they don't. And the enhanced automation does this and just returns y. So this enhanced automation solves the blow up in the example we just saw. This is the same core logic but stronger automation. The impact of enhanced automation is an approximately 1,000 speed up overall in our machine from seconds to milliseconds. And as we saw, it prevents the blow up in the test for that one contrived example, which is kind of better because instead of being a function, naive function on the number of T gates, it's a function on the T gates which do not merge, so it's a little bit better in that regard. And the proofs stay minimal. It's just validate REFL, and the side conditions remain syntactic. We apply this on quantum error correction, which is a way to protect information on physical noise. The encoders encode a single qubit to n qubits, and the code space is a subspace of the qubit space, which is a subspace of protected valid states, which can be expressed as an intersection of stabilizers, which are polystrings. The stabilizers act as quantum parity checks, where the -1 eigenvalue is signals an error, and the +1 eigenvalue either signals a quiet error or no error at all. And we check encoder correctness, which is that we ensure the circuit maps the input into the valid code space for Steane and Hoare encoders, where the Steane maps 1 qubit to 7 and Hoare maps 1 qubit to 9. We check that the input x goes to logical x and the input z goes to logical z. the Hoare triples, two Hoare triples on the bottom are for the Steane encoders, where we can see that the above, the x1 goes to the x bar, which is the logical x, and the z1 goes to z bar, which is the logical z. And the G1 intersection G6 becomes the code space. So this is checking two things at once. The first is that the input does get into the code space, and second, x does go to logical x, and z does go to logical z. The limitations is that T-gates that are spread across many qubits still blow up. This is the same for the enhanced automation case as well, because it's the structure of the logic itself looks like that. So there's no going around. And for future work, we want to support measurement with faster symbolic term structures. And we want to support quantum error correction beyond the encoders, which require measurement and conditional branching with classical variables. So the conclusion is that we mechanized and Hoare-Heisenberg logic in Rocq for low T Clifford-T circuits. We have syntactic predicates, which enables deterministic forward reasoning, and Rocq checkable proofs without external solvers. And for scalability, we have it is efficient for circuits with limited T-gates, but it blows up for many T-gates across many qubits. The enhanced automation was developed after the VMCAI artifact, so it's not in the paper, but it's on GitHub. It's in inquire/Heisenberg logic at reflexive automation branch. And we give thanks to William Spencer for making reflexive automation happening. That is all for the talk. Thank you very much.
So questions?
Thanks, Youngchan, for a nice talk. So I want to ask, like, your work is actually trying to address the case where you have a few T-gate.
Yes.
But in your example, you use encoder as an example, which has no T-gate.
Yes, that is
and
true.
that is actually sufficient to use just some stabilized simulation to handle. Have you tried any case with like interesting case with a few T-gate?
Few T-gates example. Quantum error correction is not that one. We mostly did as a stress test, we mostly did test how the additive predicates split each other, but I don't think we did an actual close to real world test on the T-gate, low T-gate style circuits.
So it's a future work, right?
Yes. Oh yes, except for Toffoli, but that's just one of the example.
Thank you.
Thank you.
More questions?
Thanks for the talk. I was wondering, so like in practice, like for a quantum algorithm that's offering quantum advantage, the T-gates must be distributed throughout a quantum circuit in such a way that like the conjugation action of the overall unitary on any poly must have a lot of non-zero coefficients when expanded in the Pauli basis.
Yes.
Like, so there must not be very much of this of this simplification that can be done. So which you acknowledged, like, in saying, but so I guess my question is kind of like, yeah, I guess about the scalability and what role this would have when looking at the size of kind of quantum programs or something that would be offering real quantum advantage.
So the first thing is that in future work we are firstly tackling the support for quantum error correction, which is stabilizer based without T-gates. So we are trying to support measurement first and with classical variables, but with multiple T-gates, examples with multiple T-gates, I will suspect that it will with more T-gates it will eventually blow up, similarly to what we just saw in the graph. Not as that bad because the enhanced automation kind of made the runtime more faster, but it will still algorithmically, I am expecting it to blow up similarly.
So, like, for instance, like, have you tried it on like the quantum Fourier transform or something like that? I would think it might blow up pretty quick.
We didn't try on the QFT yet, but that would also be as a future work.
Okay, thanks.
Further questions? We still have time. So I have a quick one. So I mean, my first impression about is Heisenberg Hall logic. You can express the separabilities
Yes.
property. Yes, but yeah, have you tried to verify some separability of some algorithms, some implementation of algorithms, or?
What was it? Sorry, I forgot the circuit, but there was an example circuit where we checked the single qubit separability. So for ancillas where we undo the computation, we can get separability for that uncomputed ancillas. It does go through, but the problem of multi-qubit separability is that the T-gates make them additive, which doesn't behave well. So just for single qubit, the uncomputed ancillas do work as an example, but we can't specify we can't specify the stabilizer states in the Gottesman tabular way, tabular style, because the T kind of blows the terms up.
Okay, thank you.
Okay.
So, no further questions. Let's thank the speaker again.